Thanks, Graham, and thank you everybody for sticking it through to the last day here. So I am going to be talking about quantifying the role of groundwater for drought mitigation in agricultural systems, specifically the Columbia River Basin. But I will preface this talk by saying I took advantage of this conference to really start a new research project. So this is really the first crack at just pulling together a number of different data sources to see first if we can even detect groundwater in the Columbia River Basin, and ultimately to set up a framework to understand climate change adaptation. But right now it's really just pulling together and playing around with different data sources. This is a picture of the Columbia River as I crossed it last Saturday. So of course everybody thinks about the river in the Columbia River Basin, but I'm going to show that the river itself is not the only source of water for agriculture and for multiple uses in the region. Just a quick background, starting with the river. It's the fourth largest river in the US and North America by flow. And this is an image of the river itself. The majority of it is in Washington, Oregon, and Idaho, but some of the flow does start in Canada. This is interesting because it established some early transboundary water agreements, starting with the 1909 Boundary Waters Treaty. This established an international joint commission for the US and Canada to jointly manage their shared resources. Ultimately, this became the Columbia River Treaty when the two countries were interested in understanding how the river could be used to increase water use across the region. What I'm showing here, I'll talk about in a little bit, but we have various stream gauges that are modeled on our river network here, and also the large reservoirs in the system that are important for flood protection specifically, and also for hydropower. The Columbia River Basin is not quite at the level of California, perhaps, for agricultural production, but there are over 300 crops that are grown in the Columbia River Basin. Most famously, perhaps, the Washington apple. I'm from Seattle, so I'm very proud of this. The apples are the largest cash crop for the region, followed by dairy. We have 2013 crop values here for wheat and for apples. And in fact, a large percentage of the hops grown in the US are also from this region. Though we have not had the drought that California has had, 2015 was a severe drought year for Washington, and because of that we saw pretty significant economic losses in crop production, which you can see for apples and wheat right here. Now, the Columbia Plateau Regional Aquifer System is a large aquifer sort of in the heart of the Columbia River Basin, and also in the heart of where a lot of the ag land is. If we go back to this land cover map here, this is from a 2015 USDA cropland data layer. The colors might not come out great, but we see all of this pink area is cropland. I just grouped all cropland together, so this is tree fruit, row crops, everything. And that's also where we see this Columbia Plateau Regional Aquifer System here. It's 44,000 square miles, about 115,000 square kilometers. And I say this because I'll be using the GRACE satellite in a few slides, and it's important to have a region that's large enough to capture variability and storage change from the satellites. Now, we have not extended our forcing data for our model, which I'll also discuss through 2015, across the whole Columbia River Basin, so I'll only be looking at the United States portion of the basin, and I also just wanted to highlight the Snake River, which is one of the big tributaries in the Columbia. The majority of the Columbia Plateau Regional Aquifer System is underlain by Columbia River basalt group units. There are about 7 main units in this aquifer system with some sedimentary deposits on top. The Grand Ronde is the main basalt unit that actually extends to thicknesses upwards of 16,000 feet. A recent USGS study found that about a quarter of irrigation water use in this aquifer system is derived from groundwater, with the remainder being met by surface water. So that's coming in at about 1.4 million acre feet on average over this time period. As I mentioned, our drought has not been as bad or as long as California's. Here on the right, we have the most recent 3 droughts in the region from the US Drought Monitor, up in the Columbia here in 2001, 2005, and 2015. We're dwarfed by California, but I don't know if that's something for California to be proud of or not. This region is largely fed by the snowpack. We think of the snowpack as an additional reservoir. So these are snow water equivalent anomalies from our model, which I'll talk about, and precipitation anomalies. This is just starting our figure in 2000, but these are anomalies with a mean from 1980 to 2015 removed. So you can see that in 2001 and 2005 in particular, precipitation was anomalously low, and our drought last year was largely driven by a reduction in snowpack. So as we look at time series to come, 2001, 2005, and 2015 are going to be the years to focus on to see if we can detect any changes in how groundwater is used or stored in those years specifically. So what tools can we use to look at the role of groundwater in this agricultural region? And does the role of groundwater change during drought? Again, this is a first attempt to pull together some different data sources, different tools, from observations to models to remote sensing, and you'll see that there are discrepancies across these sources so far. So I'll begin by talking about an activity happening at Washington State University, coupling a hydrology model with a cropping systems model. I'll show that in comparison to remote sensing observations from GRACE, and then look at additional reports and studies from the State of Washington Department of Ecology specifically, and also some reports of emergency well authorizations that are authorized during drought in the state of Washington when the governor declares drought. And the next talk will actually be focusing in on well authorizations for drought in the Yakima River. Like good hydrologists, we go back to the fundamentals of the water balance. These are two equations we can look at to estimate total water storage changes in a region, in this case the United States portion of the Columbia River Basin. And we can do this based on fluxes of precipitation, ET, and stream flow, or based on changes in storage components from surface water, soil moisture, snow water equivalent, and groundwater. Now I'm going to show how we can use these different tools to quantify different components and try to focus in on changes in groundwater storage. And to do that, we'll look at Vic CropSyst and two reservoir operations models that are coupled to Vic CropSyst, and also GRACE, as I mentioned. So we'll start off by looking at Vic CropSyst. So you may be familiar with Vic in particular. It's a land surface hydrology model developed in the early 90s. And you feed in forcing data such as precipitation, temperature, soil data, elevation, land cover, and it basically solves for the water and energy balances at the land surface. Now there is a soil zone, but there's no explicit reservoir that represents groundwater with Vic by itself. So the model produces runoff and base flow, which is then routed separately into the stream network, and then calibration is done based on observed stream flow to modeled stream flow. Now, CropSyst is a model developed by Claudio Stockel and Roger Nelson at Washington State University, and it's a biophysically based cropping systems model that basically goes through the whole crop growth cycle for a number of different crops. So these are all of the crops that we have set up Vic CropSyst for as this coupled unit, and I'll show how they're coupled next. And so you feed into the model crop parameter files for each one of these crops that represent things like growing degree days, planting date, days to maturation, additional phenology information, CO2 concentration, peak LAI, all of these parameters that have been ground truthed as much as possible for the Columbia River Basin specifically. Now, when we bring Vic CropSyst together, these two models are fully integrated, where Vic basically provides water availability and feeds that on a daily time step into CropSyst, which then produces crop water demand at the specific crop growth stage that it's at that day. And then CropSyst is producing ET, soil moisture uptake, and then it feeds that information back into Vic, which continues to route stream flow. So first, Vic is run in its natural vegetation state. Stream flow and the soil parameters are calibrated to natural stream flow with natural land cover. And then that calibrated Vic is connected to Vic CropSyst, and there's additional calibration done to crop yields produced by CropSyst. And again, CropSyst shows or quantifies yield and biomass for all of those different crops. So we can use VIT-CropSyst to quantify P, ET, and Q, as well as soil moisture and snow water equivalent. One thing that is great about using VIT-CropSyst is traditionally when we use this water balance approach with GRACE, changes in soil moisture are hard to account for as a result of agricultural activities. So with CropSyst, we're actually incorporating the influence of human management in ag lands specific to crops and also irrigation type. You can specify what irrigation type is being used for different crops in different areas. So this is actually giving us sort of a combined natural and human soil moisture change estimate. And then surface water comes from the Colsim reservoir model, which was developed as part of the Columbia River Treaty to measure reservoir storage changes and stream flow coming out of the biggest reservoirs in the Columbia River Basin. And there's a similar version of that, the Yakima Riverware model, which the next talk will also discuss. And both of these reservoir models take water demand and regulation information, flood control curves, and basically optimize water distribution out of the surface water network. So we're using reservoir storage changes from the largest reservoirs in the Columbia and the 5 main reservoirs in the Yakima to quantify this term here. I'm sure most of you are familiar with the Gravity Recovery and Climate Experiment satellite mission, jointly out of NASA and the German Space Agency. NASA is a pair of satellites that orbit the Earth together, measuring changes in the total amount of water stored on land, producing gravity anomalies that we see globally on these little spheres here. GRACE doesn't know what's soil moisture, what's groundwater, what's surface water, so it's up to us to come up with different ways to quantify these terms to isolate out what we're interested in this case, groundwater. So this is an example of what this process looks like to isolate groundwater across the U.S. portion of the Columbia River Basin. We have changes in soil moisture in the upper left, snow water equivalent, reservoir storage change, and then it might be kind of hard to see, but here we have total storage both from GRACE in the dashed lines, and then also from P minus ET minus Q, all from VIT-CropSyst. And again, if we look at 2001, 2005, and 2015, I can't necessarily say there's a huge influence on the drought in these signals. Now, this is just for the Columbia Plateau Regional Aquifer System. None of the large reservoirs are actually overlaying the aquifer system itself, so we don't have surface water storage changes here. And I'm just going to go through, and now we have estimates of groundwater storage change, both in the Columbia Basin across the whole extent in the U.S., and then the aquifer system itself in the solid lines. And again, if we look at our years of 2001, 2005, and 2015, it's not clear that there's any significant difference in groundwater storage changes in those years compared to the other years. This is, again, just a first crack at it and needs to have some additional studies done on it. This is irrigation demand modeled by the CropSyst side of VIT-CropSyst. So this is across the whole Columbia River Basin, showing total irrigation demand. The vast majority of that irrigation demand is met by surface water, about 80%, with the remainder coming from groundwater, and you see those percentages here. So this number is up in the 3 times 10 to the 5 million acre feet range. And if we compare that to the groundwater storage changes, the groundwater storage changes are an order of magnitude greater than the irrigation demand. It's comforting to know that when there's irrigation demand, we have a loss in groundwater storage, but that's not to say at this point that they're directly related to one another. The Washington State Department of Ecology has an extensive project called the Forecast Project that every 5 years re-quantifies supply and demand across the state of water. And they recently, for the first time ever, had some estimate of groundwater influence in the state of Washington, especially based on the drought last year. So these are the subregions that have the dominant groundwater declines seen in the state of Washington. The Odessa subregion here has declines up to 25 feet per year in the past couple of years. But sorry about this, it's hard to see. It's just really a small chunk of the state. So the next step would be to look at their information and additional observation wells and see how this data scales up to some of the signals we're seeing at a larger basin scale. The State of Washington Department of Ecology also released to us some authorizations, permits for emergency drought well use. Again, when the governor declares drought, that opens up a series of emergency wells that can be tapped often by junior water rights holders. This is the number from the 2001 drought. This is the total acre feet that was returned back to the Department of Ecology from the permits that were applied for. So we don't know how much additional groundwater use there was from these permits that weren't returned to the state. This is 2005, and they told us that only about a third of the permits are back from 2015, but these numbers are all over the place, especially when you consider the magnitude of both irrigation demand for groundwater and of groundwater storage change that we found with VicCropSyst and GRACE. These little dots here show where the permits were returned for this 2015 number here. So in summary, by throwing together a few different types of information, we're trying to understand how groundwater might be playing a role in the Columbia, but there's not really consensus yet. So my next step is to take all of these wells that have at least one point of record since 1980 in Idaho, Oregon, and Washington, and kind of use those observation wells as an intermediary between what might be happening on farm and what might be happening at the bigger GRACE basin scale. Now I'm going to preempt some comments about the spatial scale of GRACE. Why do we even care about looking at a scale this large? Well, I think we heard this morning when you're talking about how to communicate some of this information up to higher level decision makers, it often comes down to having a single number to give to them. So you can't go through every single deposit of or location of groundwater depletion in a region, but be clear to inform them that that information is transferring up to the GRACE scale. So we're trying to use this pretty well-studied region to understand how the GRACE scale comes down to observation wells and back up. And there's a lot of great work being done with data assimilation, artificial neural networks to downscale GRACE, and that will all be part of this in the long run. But I think that if California looks to Australia to see how its future might be, Washington can look to California to see what its future might be, both for education funding for public universities and also for groundwater. So if we can start thinking about a framework to understand groundwater in this region now, then hopefully we can plan for it in the future. And with that, I'll stop. Thank you.
And then instead of saying, okay, the rest, what we see in GRACE, the rest is the groundwater, but just, I mean, for example, the lowermost layer of Vic, I mean, that is like the groundwater because they produce base flow out of it. So you take out the groundwater that you think you want to take out, and then you can compare everything together.
Yeah, that's definitely the direction that we want to move toward. So Vic right now does not have any vertical exchange of fluxes with a groundwater system, but we do want to move to that. The work at Washington State University thus far has been focused on surface water modeling and crop modeling, and now we have a new team of a few different groundwater people, and we're interested in doing just that, and we can look to your work to understand how to do it best.
I think there's a groundwater model of that region, and a groundwater model is a process-based model that actually built into it relates changes in groundwater levels to changes in storage. Why not use that as a tool? You mentioned the need for ground truthing there in the second bullet. Why not use that as a tool for ground truthing or translating the water level change data in the wells to change in storage?
I'll take an easy answer on that, which is, as I mentioned in the beginning, this is a very early project, and we definitely want to move toward that, and we have some contacts at the USGS office that conducted that study, and we can use their three-dimensional model, which was recently developed. So we'll get there, and I think that's a great foundation to connect in to VicCropSyst and the more surface focus of the modeling activities thus far.
Good, thanks.
Yeah.
Hi, great presentation. So I guess this is exciting because the Columbia River Treaty is being revisited both by Canada and America. Because of that, why not embrace the Columbia River Basin both in Canada and America so that your results can really contribute to the revision of that treaty? Is it more data-driven, that it's more accessible to reach that data within America than in Canada?
So that's a great question, and it's really just the timeline of this presentation for when we were able to get the forcing data in Canada. So the majority of our work has been looking at the Canada portion also, and we have those runs through 2011, and so we're just waiting for updated forcing data to extend it into Canada. And actually a lot of the work that has been developed here with BitCropSyst and CalSim, the reservoir model, is part of understanding how the Columbia River Treaty might change. So in 2024, the current mandates in the Columbia River Treaty are going to be revisited, and Canada's requirement to provide flood control as part of the treaty will be changing. So we have people in our group who are looking at that treaty and trying to understand different options for how it could be reworked. I would just say we should have groundwater in that, using what Graham and Petra have mentioned also. Thanks.